Hi, I'm Zhang, and I will present our work, Faster and Cheaper Serverless Computing on Harvested Resources. This work is done with Microsoft Research. I'd like to start with a brief introduction to serverless computing and harvested resources in data centers. First, let's look at serverless. From the user's angle, serverless is an attractive abstraction with pay-per-use pricing models, and users don't need to worry about VM management. However, from the service provider's angle, providers do need to provision, manage, and pay IaaS providers for hosting VMs. This ties the cost of serverless to the cost of underlying VMs. Now let's look at harvested resources in data centers. Data centers are usually underutilized. The figure shows the resource underutilization of a Google cluster. As a result, IaaS providers offer their surplus resources as VMs at a much lower price. Along similar lines of work, Microsoft recently introduced harvest VMs, which are low-priority VMs that are able to grow and shrink to harvest all the unallocated resources on the host. In order to reduce the operation costs of underlying VMs and to provide a faster and more efficient serverless product, we propose to host serverless computing on low-cost harvest VMs. To understand the challenges and feasibility of hosting servers on harvest VMs, as a first step, we need to perform a characterization study for both harvest VMs and serverless workloads. For harvest VMs, we mainly care about two things, which are VM eviction and VM resource variation. VM eviction translates to reliability, and resource variation translates to performance. We first look at the VM lifetime. The left figure shows the CDF of harvest VM lifetime. We can see that more than 90% of the harvest VMs live longer than 1 day, and more than 60% of harvest VMs live longer than a month. So intuitively, most of harvest VMs are not short-living, and evictions are generally infrequent. Then let's look at resource variation. The figure shows the CDF of harvest VM CPU change interval. As shown in the figure, 70% of change intervals in the red region are longer than 10 minutes, and 35% of intervals in the orange region are longer than an hour. Compared to VM evictions, VM resource variation is much more frequent. Thus, the implication is that in order to fully utilize the resources, proper load balancing is required. For serverless workloads, we care most about the relation of invocation duration and VM eviction grace period. If an invocation is shorter than 30-second grace period, we can always safely terminate. Thus, we call an application long invocation if it is longer than 30 seconds, and short invocation otherwise. In Azure function, application is the unit of scheduling and resource allocation. Following the same logic, we define long applications to be the ones with at least one invocation longer than 30 seconds. The left figure shows the CDF of invocation durations in the serverless workloads. So 96% of all the invocations are short invocations. So most invocations are short. However, if you examine the breakdown of total execution time, it turns out that long invocations take over 82% of the total execution time. If you look at the trace from the application's angle, the trends are exacerbated. 48.7% of the applications are long applications, and these long applications take over 99.7% of total execution time. In the end, the intuition is that nearly half of the applications are long, and these long applications take over almost all the execution time, or in other words, computation power. To summarize, the main takeaways from the characterization study are threefold. First, intuitively, serverless workloads are good fit for harvest VMs because most invocations are short, and also because VM evictions are relatively infrequent. Second, harvest VM resource variation are much more common than evictions, requiring proper load balancing to fully leverage the resources. Third, long applications take over almost all the execution time or the computation power. Since we are convinced that serverless workloads fit harvest VMs well, our immediate challenge is to eliminate or to minimize invocation failures caused by VM evictions. The natural idea is to use a mix of low-cost harvest VMs and reliable regular VMs. To this end, we study three strategies that make different trade-offs between reliability and efficiency, which are no-failure strategy, bounded failure strategy, and lastly, the leave and let die strategy. So now let's look at the three strategies. The first one is the no-fear strategy. It guarantees no eviction-induced fear by assigning all the null applications to regular VMs. Since this strategy offers the best reliability, we are only concerned with efficiency. Unsurprisingly, the efficiency is unsatisfying, with only 12% of computation hosted by Harvest VMs. This matches the intuition from the characterization that almost all computation power are taken over by null applications. So we've seen that offering 100% of reliability is expensive. So let's look at bounded fear strategy, which provides an upper bound on the fear rate by bounding the fear rate of each application. If you want to bound the fear rate by 100 minus X%, we check the X duration percentile of each application and assign the application to regular VM if it is longer than 30 seconds. Since we have a well-defined upper bound on fear rate, we ask the same question on efficiency. Essentially, bounding the fear rate by 1% allows 45.7% of computation to be hosted by Harvest VMs, and bounding the fear rate to be less than 0.1% allows 28% of computations to be hosted by Harvest VMs. In summary, although efficiency improves compared to the no-fear strategy, it is still pessimistic, because most invocations that run in regular VMs are still short. Lastly comes the leave and let die strategy, which allocates all the applications to Harvest VMs. This strategy is clearly the most efficient, but lacks a theoretical bound on fear rate. So this time we ask the question on reliability. The actual invocation fear rate turned out to be very low. In the worst case, the serverless platform achieves 4 nines of reliability, and in the typical case, it achieves 7 nines of reliability. The actual invocation fear rate is low, because fear requires 2 low probability events to happen simultaneously, which is that a Harvest VM gets evicted while it is running a non-invocation. To summarize, the no-fear strategy is very conservative and causes most of the computation to be hosted by regular VMs. Bounded fear strategy improves the efficiency, but is still pessimistic. The leave and let die strategy, although lacking theoretical bound, delivers the best efficiency and actually low fear rate. As a result, in the rest of the presentation, we will stick to the leave and let die strategy. The frequent resource variation of Harvest VMs implies that proper load balancing is required. We use join the shortest queue as the start point of our load balancing design. Although join the shortest queue optimizes queuing and execution time, it increases co-starts because invocations of the same applications are distributed across all the VMs, making interval time of consecutive invocations to be longer than the keep alive, forcing co-starts. To optimize the co-start, we propose a new load balancing algorithm, the mean worker set algorithm, whose intuition is to consolidate each application to a minimal set of backends. Thus, the interval time can be minimized. Besides, we also adopt consistent hashing to minimize the reshuffling of home VMs upon VM eviction and redeployment. We implement the proposed algorithm on OpenWhisk, an open-source serverless platform developed by IBM. The architecture of OpenWhisk is shown in the right-hand side figure, and the dotted lines highlight our changes to the system. In general, we modified OpenWhisk to track the eviction signal and resource variation, and also to implement the mean worker set algorithm. For evaluation, we deployed OpenWhisk on Azure, and we proved the benefit of mean worker set load balancing. That mean worker set achieves more than 22x throughput of vanilla OpenWhisk. We also proved the efficiency of Harvest VMs. The Harvest VMs can achieve up to 9x throughput of regular VMs under the same cost budget. And lastly, we demonstrated that Harvest VMs are superior to Spot VMs, which are another resource harvesting VM, in terms of reliability, capacity, and price. More details can be found in the paper. So this concludes my talk, and in conclusion, and in summary, we propose to host serverless platforms on Harvest resources. We quantify the challenges of using harvested resources for serverless invocations, including Harvest VM eviction and resource variation. We demonstrated reliability of hosting serverless workloads on harvested resources, and we also demonstrate the performance and economic benefits of hosting serverless platforms on harvested resources. So this is the end of my talk, and thank you for your time.